Hi, I hope all is well with you. Today we actually begin probability and stats, but we need a little bit of math from last time. Here's one way to write down derivatives of vectors with respect to scalars, derivatives of scalars with respect to vectors, and vectors with respect to vectors. Let's start with a vector. It's actually a column vector y. You can see n rows, one column. And I'd like to differentiate respect to a number x. Depending on which textbook you read, you may have seen different expressions, but here's what we're going to use. If you want to differentiate a column vector y with respect to a number x, it's helpful to rearrange the column vector y so that you list the elements of y as a quote-unquote row vector. And now you want to differentiate each of these elements of y with respect to a number x. So what you'll do is you'll form a row vector. First element of y with respect to x, all the way to the nth element of y with respect to, these are the derivatives then. Now you want to differentiate y, which is a scalar, with respect to a vector x. So it's almost like in the first expression up here, there is no y2, y3, and yn, just simply quote unquote y1, or just simply plain y. If you want to differentiate with respect to a vector x, it's helpful to write the vector x that you're differentiating with as a column. And now what you do is you follow this rule: dy dx1, dy dx2, and so forth and so forth and so forth. You can quote unquote combine these two rules so that now you're differentiating a vector y with respect to another vector x. So it's helpful to use the first line because there what you did was you listed the elements of y in a row. And now you have to remember that you're differentiating each of these elements with respect to quote unquote the x, which now the x now consists of a column vector. So the only modification you now have to do is, instead of saying dy1 dx, you now say dy1 the whole column vector x, which by the second rule that you just did right now will then become a column vector unto itself. So dy1 dx1, dy1 dx2, and so forth. You do this for the entire y1 element, same thing with y2, all the way to yn. You can see dyn, dx1, dyn, dx2, and so forth and so forth. Using these rules, let's see now what actually happens if you do this derivative. Here's a vector c consisting of constants, c transpose times x. C transpose times x is going to be, if you look at this right here, it's a 1 by n vector times an n by 1. So you know the answer has to be 1 by 1 or a number. So it's basically now summing up this thing right here. This is simply the sum. And same thing over here. X transpose C is again going to be a sum, 1 by 1 sum, the sums of C's times the X's. Now what you want to do is, here's a derivative of a scalar, right? Just like we saw 2 seconds ago, with respect to a vector. So the rule was d scalar times each of the elements of x, x1, x2, and so forth. So I differentiate the scalar with respect to x1, and keep going until I differentiate the scalar with respect to xn. If you take the sum right here and differentiate with respect to x1, you'll pull out c1. If you keep going down, with every line you're going to pull out the c1, c2, c3, all the way down to the last row, which is cn. So what you get back, of course, is the vector c. So you have a nice rule. The derivative of c transpose x or x transpose c is always c. What about the derivative of the matrix A, n by n, times x? This is n by n times an n by 1, so the answer is going to be n by 1. So what you have is n rows, each of these are sums. You should really sit down and make sure that you can follow this, what's going on here. You do the first row times the x vector, second row times x vector, and so forth. So you should read the notation very carefully. Maybe I made a mistake, maybe I didn't. So now you're going to use that rule where you're trying to differentiate a vector with respect to a vector. So it's helpful to write down those those elements of vectors as a row form. So here's the first element of the y vector, second element of the y vector, and so forth, the nth element. Differentiate respect to the column vector x's, which now, if you remember, when you differentiate, carry out this thing, it becomes a column vector like this, like exactly obeying those rules right there, and so forth. This gives you an n by n matrix. If you actually do the math and expand this out, and you do differentiate respect to x1, you will see the answer is A11. And so you should verify that what you get back is, of course, if you look very carefully, this is A11, but that is AN1. And this is not AN1, it's rather A1N. So this is, of course, a transpose of A matrix. Only way to do this is to make something up. Let's say you take a 2 by 2 matrix, carry out this derivative, and you convince yourself this is in fact A transpose. What about X transpose A? So I think you kind of get the hang of it, right? So how to do these sort of things. So using these rules as we showed earlier, you can convince yourself that the answer is the matrix A. And finally, one really important thing, of course, is what's the derivative of X transpose AX with respect to X? This should look mighty familiar. This is nothing but the quadratic form. The quadratic form, you know, is a scalar. So in the end, what you actually are saying is, give me the derivative of a scalar with respect to a vector x. Very simple. Going back to the rules that we did earlier, you'll differentiate a scalar with respect to x1, x2, and so forth. So that's exactly what I've done here. I've differentiated the scalar x transpose x, ax, which is a quadratic, with respect to x1, x2, x, and so forth. If you write out the general form, you should go to lecture B2, I believe. At the very end, I gave you the general form of a quadratic. That's where I pulled these expressions from. So you want to now differentiate this long animal with respect to x1, x2, and so forth, and so forth, and so forth. To make it easy, why don't you imagine that A is a 2 by 2 matrix? In that case, those expressions you saw on the previous slide become something much cuter. You should convince yourself that you can do this, okay? Like this. So this is the quadratic form for A when n is equal to 2, whereas you have x1 and x2 as the only two variables. What I've done is I've actually carried out this derivative and gotten this thing right here, and I purposely broke it up in these two parts. And then I noticed that if I re-express this first term this way, the second term that way, I notice that this is, of course, the matrix A times X, the matrix A transpose A times X. So now you have a general rule that gives you this thing right here. It's vital that you practice the following for this Friday's test and, of course, for econometrics. Summary is right here. Here's what we want you to practice. Here's a classic cross-sectional OLS model, ordinary least squares. You now have you have k x variables, kangaroo, plus an intercept. So the actual number right inside variables is k plus 1. If somebody had to reimagine an Excel spreadsheet with what the data would look like, beta 0 corresponds to a bunch of ones, beta 1 corresponds to this column of data right here, etc., etc., etc. So you can write down this OLS model as y is equal to x beta plus epsilon. OLS, ordinary least squares, says minimize sum of squared errors. Of course, by now you have a pretty firm grasp of how vectors work. So that'll be E transpose times E. That's exactly what you see here. But of course, you know that E is y minus x beta from the previous slide. Right? So you can express epsilon as, or E I should say, as y minus x beta. So of course, when you do this, you do it like this. You now remember the rules of transposes. I hope you remember those things. Multiply the whole thing out, and then you get this thing right here. Expand, expand, always now I'm now using the rules of transposes. This part is very important, not to be something that you would remember in real time on Friday. I brought it over here, and now I've applied these rules. You notice that there is no beta here, so there's 0 over here, right? So this will become 0. I'm now using the rule, if you look very carefully, this takes the form a matrix A times beta. That's your AX rule over here. So you should apply these rules and make sure that you get this expression right here, which of course rearrange will then give you something like this. This is also, by the way, known in econometrics as normal equations. And of course, when you rearrange all this stuff, you get the OLS vector. X transpose X inverse X transpose Y. Extremely important. Let's go to probability now. The world of probability is a world of imagination. Nothing that I say in this lecture is going to be something to do with reality. You won't hear words sample means, you won't hear sample medians, modes. We're not doing hypothesis testing, nothing of that sort. We're sitting in an armchair and we're trying to imagine something that is non-deterministic. And you choose what's not deterministic, what is up to your imagination, and you choose which variables are going to be of interest. Let me make it more interesting for you. Imagine that you toss a coin, and the only thing you care about is heads or tails. Okay, that's one experiment. Second experiment, I again toss a coin. I again care about heads and tails, but I also care about how many times the coin bounced or once it hit the floor. I can make it more complicated. Not only do I want to know heads and tails, I also want to know the number of bounces, and I also want to know the temperature of the coin when it came to rest, etc., etc., etc. So you can see the probability really boils down to your imagination. What is that you want? What is that you want to make stochastic, and what are the variables that are going to be of interest to you? Once you do this, the rules of probability take over, and they can only work if you specify something called sample space. Sample space has to list every single outcome. They have to be mutually exclusive, meaning that no two outcomes are joint. Right? Collectively exhausted means that you have listed every single possible outcome. And so an event space would be a collection of outcomes, whereas a sample space would list every single outcome uniquely without any quote unquote intersections or outcomes joined together. Here's an example. I imagine that a stock can either only go up price or the price can only go down. There's no such thing as staying constant. And I imagine the stock is moving over 3 periods. So you can, of course, in period number 1, go up or down. Same thing in period number 2, up, down, up, down. So when you list every single possible outcome over 3 periods, you see that there are only 8 different possibilities. Right here. 1, 2, 3, 4, 5, 6, 7, 8. This is literally the sample space. The listing collectively exhaustive, mutually exclusive, finest grain listing of all possible outcomes. This is the sample space. And the event space would say, possibly, that it could lump some of these outcomes in the sample space into a set. So, for example, here's event A and event B. You can see that in event B corresponds to a description where the price never went up in any period, whereas in event A can be described in words as the price went up in at least one period. Here's a different example. DJ Tiesto, who by the way sucks, is somebody who once a month withdraws anywhere from $0 to $400 from the bank machine. Okay. And his returns in dollars will never be between more than what he invests. So for example, he could withdraw any amount of money between 0 and 400, but once he withdraws any amount of money, his return will be anywhere from $0 to maximum of how much he withdrew, because you can see this is a 45-degree line. So for example, if he actually withdraws 400, his returns could be 50, 100, 200, 300, 400, but never be more than 400. So for any amount of money that he withdraws, the maximum return, his actual return will be anywhere from 0 to the amount that he withdrew. So event A now corresponds to those instances where he withdrew some amount of money between 0 and 400, but his returns in dollar terms was half of that amount that he took out, right? Because this line, this number is 200, so any amount would be, if you take X dollars out, this would be at most X over 2. Axioms of probability. I think these are pretty straightforward. You must have seen them as an undergrad. These are, I'm going to use funny notation. So this says, once you give me a sample space, by definition, the probability of all points in that sample space should be equal to 1. It sounds silly, but you'll notice in a few minutes it becomes very useful when we start doing integrals. The probability of any one outcome is always going to be between 0 and 1. For that matter, the probability of any one event is always going to be between 0 and 1. If two events A and B are not mutually exclusive, which means there's some overlap, then the chance that you have an outcome that's sitting in A and or in B is going to be like this. This is my notation. Undergrads see when somebody says given the chance something is in A and or B, they use this weird symbol, A cup B. I'll use this symbol. When you see in the exam or in this course chance of A plus B, it's understood that you mean an outcome that's either in A or B or both A and B. And by definition, that's going to be equal to, and you see why, the chance of something in A or B or A and B is the chance in A plus the chances in B. But by doing this, you've counted outcomes in A and B twice. So you have to subtract off outcomes in A and B. And that's my notation for the probability of something in A and B. Most textbooks use this notation, A upside down cup, right? So this is chance of A and or B. This is chance of A and B. And I'm going to assume that since they're not mutually exclusive, that this probability of A and B is not 0. If they are mutually exclusive, you will find out the chance of A and or B by, of course, simply summing up the chance of A plus chance of B, because this number here is equal to 0. I'll do Bayes' rule in a few seconds. This says somebody tells you that an outcome is sitting in event B. Given that an outcome is in event B, what then was the chance it's also in event A? Chance of A, given it was in B. By Bayes' rule is found by the chance of A and B divided by the chance of B. And we're going to find out that if two events are independent, then the chance of A and B can always be expressed as chance of A times chance of B. Anytime this is mathematically true, that means that A and B are independent events, in the sense that I'll explain in a few minutes. So let's go quickly through the rules. Okay, so here is 19 dots. The probability of all these 19 dots together is 1. 19 dots in all. The chance of observing any one dot is 1 over 19. The chance of observing a dot in this event set A is 3 dots over 19. 20 dots. What's the chance that a dot is in A and or B? Take the probability of A plus the probability of B minus the probability of A and B. And then the answer is 8 over 20. Here, A and B are not mutually exclusive. So the rule says, what's the chance of an outcome in A or B? Right? So take the probability of A plus the probability of B. If you want, you can subtract the probability of A and B, which of course is here 0. And again, the answer is 8 over 20. This is really important. I think it's one of the most fundamental and results in probability. This is in fact going to be, I don't know how to say this, but pretty much the foundation of econometrics in grad school. And it's done in a very weird way. Let's put it this way. You have a total of 20 dots. Somebody is sent out and asked to pick a dot from one of these 20 dots. They pick a dot that's somewhere in set B. So they either pick a dot, they observe a dot, either this one, or this, or this, or this, and this. So you told them, listen, why don't you go out and pick a dot from the sample space? They, in reality, have picked a dot from a set B. And what they do is they send you a message. They tell you, listen, hey, Ajaz, I've seen a dot, and that dot is sitting in set B. Given that you told me that you have seen an outcome in set B, what's the probability that what you saw was also in set A? So remember, you're only telling me that what you have seen is sitting in set B. from that information that you gave me, I want to know what's the chance that what you saw was in set A. One way to do this without Bayes' rule is to realize that you had 20 dots to begin with, but when you saw something in set B, this entire probability space collapses into this circle right here. There were 20 possibilities before, but the fact that you now tell me that you saw something in set B means that this is for all practical purposes the sample space. And now if the question I want to ask is, if you have seen one of these 5 dots and I want to know what's the chance that that dot is in set A, I count how many dots are in set A and B, 1, and I divide by the number of dots in set B, 1, 2, 3, 4, 5. So without Bayes' rule, I could have gotten 1 divided by 5, as long as you understand how to compress sample spaces into something that's becomes smaller. With Bayes' rule says to find the chance of A, given that it was in set B, take the chance of A and B in the big raw sample space together and divide by the chance of B in the big giant sample space together. So what's the chance of A and B together in the big giant sample space? That was simply 1 divided by 20. What was the chance of B originally in the big giant sample space? It was 5 over 20. And Bayes' rule then says take 1 divided by 20, A and B, divide by 5 over 20, chance of B, and it gives you 1 divided by 5, which is exactly what you've gotten had you not used Bayes' rule. Why is Bayes' rule so important? Here's a question I'm going to ask you very quickly. Right? Imagine that you might remember those things called independent outcomes, independent events. And I often ask students, is independence a good thing in probability or a bad thing? Time and time again, students say it's a good thing. Actually, it's not a good thing in the following sense. You have 20 dots in all. I send somebody out and I ask them to pick a dot. They send me a message back saying that they've picked a dot in set B, somewhere in the circle. Given that what they've picked something in set B, what then is the chance that what they also saw was in set A? By Bayes' rule, that's going to be 1 divided by 5. 1 outcome, or 1, 2, 3, 4, 5 dots. Agree? Now, had I not used Bayes' rule and simply asked to guess what's the chance that what you saw was in set A, be careful. What you did 2 seconds ago was you picked something and you sent me a message. Ajaz, I've picked something in set B. I'm curious that given the fact that you picked something in set B, what was the chance of an outcome that you saw in set A? So I'm practically asking, what's the chance of something in outcome in A, but given the fact that you saw it also in B? It's simply 1 by 5. If I now change the question and say, what's the chance that the outcome that you saw is in set A? I would then say, well, there are 4 outcomes that could possibly happen in A. You have picked some outcome in the sample space. So the chance that what you saw was in set A was 4 divided by 20, or 1/5. Notice these two answers are exactly the same. If I repeat the exact same experiment again, I ask you to pick a dot, you pick a dot in set B. I then have to guess what's the chance that the dot you saw was in set A. Bayes' rule says 1 over 5, 1 over 5 things. And if I have to simply guess that what's the probability of the outcome that you saw also being in A, the answer will be 4 over 18. Here the two answers are the same. Here the two answers are not the same. So the question was you sending me a message that, hey, you saw an outcome in event B useful or useless? In which of these two cases? And the answer is here, you telling me that you saw an outcome which was in event B was completely useless when it came down to predicting the chance of the outcome being in set A. Because had you not sent me the message and I had to guess what's the chance that the probability of what you saw was in set A, I would have said 1 over 5. If you sent me a message that what you saw was in set B, and I have to again make a guess that what you saw was in set A, the answer is 1 over 5. So you telling me that you saw something B was of no consequence whatsoever. Here, If you had not told me that what you saw was in set B, I would have guessed the chance of what you saw in being in A was 4 over 18. But in light of what you said, that you saw something in B, and if I have to now guess that it was in set A, the probability is now 1 over 5. Now, the fact these two numbers are different means now you telling me this in set B is in fact useful information. So, in some sense, independence is not good. Let me make this concept a bit sharper. Oops. Which is, notice how two events are called independent if the joint probabilities can be factored out as individual probabilities. If it is always true the chance of A times B is equal to the chance of A times the chance of B, you have independent events. And by the way, one implication of this is that therefore using Bayes' rule, if two events are independent, the chance of A in being B is simply equal to the chance of it being in A, which is exactly what you see over here. So, right? So if two events are independent, it tells you that you telling me that event B has actually happened gives me no useful information in terms of predicting the chance of something being in A. I might as well have used the initial probability of A to begin with. Random variables. Since we want to use mathematics, what you want to do is, if we had a sample space consisting of discrete, literally discrete outcomes, we would have some function that assigns a number. So with every outcome, I'm going to assign some number, and those numbers are called random variables. It's called random variables because you don't know which outcome is going to happen, which outcome is going to be picked. It's a stochastic process. Therefore, you don't know which of these values is going to be picked. This picture is not quite right, but if the sample space was quote unquote continuous, consisting of an infinite number of dots, once again we could have a rule that assigns each of these dots in the sample space to a number on the number line. An example. Here's a sample space of following a stock price up and down over 3 periods where the price can only go up or down. 8 possible outcomes. Let's define a brand new random variable. Baby U is the total number of up price movements over 3 periods, and baby R is the length of the longest successive run of either up or down price movements. Once again, baby U is the total number of up price movements. Let's take the first one here. What's the total number of up price movements? 1, 2, 3, 3. Total number of up price movements, 2. Total number of up price movements, 2. Total up are 1. Total up are 2, 1, 1, 0. Length of successive run of either up or down price movements. So what's the longest successive run of ups and downs? Well, you can see 3 ups in a row, that's 3. The longest successive run was 2 ups. The longest successive run was, you can see, up, down, up. So the longest successive run was in fact just 1. Here, the longest successive run is of either ups or downs. Well, 2 downs, so that's 2. 2 ups, so R is 2. 1 up and 1 down, so that's 1. The longest successive run is, again, 2 downs, 2. And now you're 3 downs, so of course, it's 3. So now with every sample point in the sample space, you have defined a unique number for random variable baby U and random variable baby R. We now go to PDFs and PMFs, probability mass functions and probability distribution functions. I'm going to talk about mass functions, which are essentially probability distributions for discrete random variables, by going deliberately this way. I'm going to ask, give me the joint distribution. What's the joint probability of having a random variable x take on a particular value baby x and the random variable y take on a particular value baby y? So this expression refers to the property of observing a certain value of x and y. By definition, the total probabilities always have to add up to 1. So when I sum across the x's or y's, I know this sum must be 1. Let's take an example. So here, what I've done is I've taken all those 8 outcomes in the sample space of ups and downs price movements. And for your convenience, here are the different values of u's different values of r's, and these are the probabilities. You have to make sure you get this. So for example, each of these numbers is 1 over 8. There's only one way out, let's see. So you want u0 and r1. So where's u0? Here's u0. And where's r1? There's no r1, right? No u0, no r1. The chance is 0. What about u1, r1? So u1 is right here. See, 1 dot right here. And what about u1 and r1? So that's not u1, r1. That's not u1, r1. This is u1, r1. So there's only one outcome corresponding to one u1, 1, r1, 1. So that's, of course, 1, 8. And by going by this logic, you build up each of these things as pillars. So you can imagine now that these are literally the heights. So this is 1, 8, 1, 8, 2, 8s, 2, 8s, and so forth. These pillars are literally telling you the probability of observing a certain value of u's and r's. When you work in discrete random variables, and that means you're working in probability mass functions, heights are the probabilities. I'm now going to go from joint probabilities to marginal probabilities, which basically means that this is very extremely important expression. To get just here you have both the probabilities of u's on the x-axis and the probabilities of r's. Sorry, my bad. U is on the x-axis, R is on the y-axis, and the z-axis gives the probability of quote-unquote x and y. If you're given the probabilities of quote-unquote x and y's, how would you get just the probability of the x's and just the probability of y's? This formula is not going to make sense unless I do an example, but let's read it out. To get just the probabilities of x's, take all the joint probabilities of x and y's and sum across all possible values of y. And if it's a legit distribution, those probabilities of x's then summed over all the values of x's must be equal to 1. To get the probabilities of y's, take the joint probabilities of x's, sum across all possible values of x's. Once I get those probabilities of y's, if I then sum across all the possible values of y, those must add up to 1. Example. What you're trying to do is look at it this way. So here is u on this axis, here's r on that axis, and those are the probabilities of u and r. What you want to do is you don't care about the values of r anymore. You want to imagine looking at this graph from the u-axis perspective, and you wonder if I collapse this entire picture onto the u-axis, what would the probabilities of u's look like? So you basically what you do is you want to collapse all these pillars into u is equal to 0, these pillars into u is equal to 1, those pillars u is equal to 2, those pillars into u is equal to 3. And you can see so this is what you meant by summing across all possible values of the other variable. So let's try it again. To find out the probability of simply observing u is equal to 0, u is equal to 0, I sum up all these probabilities going across this way. So this is literally the joint probabilities of r and u sum across all possible values of r. So sum this way comes 1 over 8. The chance of observing u is equal to 0 is 1 over 8. 1 over 8. The chance of observing u is equal to 1 is sum these probabilities of 3 over 8. 3 over 8. Probability of observing simply u is equal to 2, sum these probabilities of 3 over 8. 3 over 8, 3 over 8. And of course, the probability of observing simply u is equal to 3, sum across all possible values of r, 1 over 8, 1 over 8, 1 over 8. In the same way, I can look at the graph from the r-axis perspective. And I wonder if I were to sum across all these, or to collapse all these pillars onto this axis, what would the total height of these pillars be? This way. So I can see that what's the probability of r being equal to 1? Take the joint probabilities of r and u, sum across all possible values of u. So I'm going this way, 2 over 8. So chance of r being equal to 1 is always 2 over 8. 2 over 8, that's exactly what you see over there. So r is equal to 2, sum across joint probabilities for all possible values of u, 4 over 8. 4 over 8s. And what's the probability of r is equal to 3? Sum across all possible values of r. And the answer is 2 over 8, 2 over 8, 2 over 8. So this gives you the expression that we just did right now. Once again, coming back to that thing about summing up to 1, notice that these probabilities add up to 1. If they didn't, it would not be a legit distribution. If I go back one previous slide, those probabilities also add up to 1. If they didn't, it would not be a legit distribution. Conditional probabilities. This says, well, it says give me the probability of x given that the probability that y takes a certain value, baby y. You're actually asking not for a number anymore, but you're asking for distributions. And what that means is something along the following lines. These are the joint distributions, right? The joint probabilities. Literally, this means there's a 2/8 probability that r will be equal to 2 and u will be equal to 1. What you want to now do is you want to imagine that somebody is sent off and they are asked to pick some value of some outcome. They're asked to just pick one of these, 1, 2, 3, all these numbers, right? So they can, in reality, they can only pick numbers with positive probabilities, either this one or that one or this or this or this or this, right? So, for example, they may pick something where r is equal to 1. And I want to know, given the fact that you have picked something where r is equal to 1, what then is the probability of u being equal to 0, or u being equal to 1, or u is equal to 2, or u is equal to 3? So the fact that you've told me that you have picked r is equal to 1 now means that this green rectangle in its own right is a probability distribution. So what's the chance by Bayes' rule, what's the observer, given that r is equal to 1, what's the chance of u being equal to 0? Well, u, 0 divided by 0. Given that r is equal to 1, what's the chance of u being equal to 1? Well, the sum of these numbers was, you can see, 2/8. So given that r is equal to 1, what's the chance that u is equal to 1? 1/8 divided by 2/8, which of course is 1/2. What's the chance that u is equal to 2? Given that r is equal to 1, 1/8 divided by 2/8, half. By the same token, you can see that what's the probability of u being equal to 0, given that r was equal to 2? 0. What's the probability of u being equal to 1, given that r is equal to 2? The total probabilities add up to 4 over 8. So the chance of this one will be 2/8 divided by 4/8, which is 1/2. 2/8 divided by 4/8, 1/2. And this one, the probabilities add up this way, sum up to 2/8. So this is 1/8 divided by 2/8, so 1/2. 1/8 divided by 2/8, so 1/2. So this would give you, in their own right, these are literally conditional distributions. The probability of u given that r is equal to 1. Probability of u's given r is equal to 2. Probability of u's given r is equal to 3. In the same way, you can find out the probabilities of r's given a certain value of u. So if u is equal to 1, what then is the probability of r being equal to 1, r is equal to 2, r is equal to 3? Since there's only one outcome here, this will be 0, 0, and 1/8 divided by 1/8, of course, is 1. The sum of these things is 3/8, so that'll be 1/8 divided by 3/8, which is 1/3. 2/8 divided by 3/8, which is 2/3. Sum of these things is 3/8. 1/8 divided by 3/8 is 1/3. 2/8 divided by 3/8 is 2/3, and so forth. And you should, of course, figure out that on your own and see that's in fact equal to 1. So this gives you the probabilities of r, conditional probabilities of r given different values of u's. Now, by what we said earlier about, right, so two random variables are said to be stochastically independent if the probability of x and y can always be factored out as the probability of times x times y. If I can go left to right and right to left, it means x and y are stochastically independent. And of course, quote unquote, using Bayes' rule, if the chance of y given x is always equal to the chance of y, they are truly or statistically independent variables. So for example, Do you think R and U are independent? So let's pick some number. Let's see. Let's actually pick, I'm going to do something right here. Let's actually pick this thing right here. This is the probability of R being equal to 2 and U is equal to 1. Agree? I want to know if the chance of R being equal to 2 and U is equal to 1, which I know is 2/8, is that equal to just the probability of R equal to 2 and just the probability of R U equal to 1? So what's just the probability of U equal to 1? Just the probability of U equal to 1 is 3/8. That's this thing right here. And what's just the probability of R equal to 2? That's going to be equal to right there. Agree? I wonder if 3/8 multiplied by 4/8 is equal to 2/8. Well, no, right? Because that's just not true, right? So 3 over 4 is 12. 8 times 8 is 64. 12 divided by 64 is not 2/8. I hope. Is that right? I think so, actually, yeah. Um, maybe we should do one more. Okay, fine. What about this one? Here's the probability of R equal to 1 and U is equal to 2. Is that equal to just the probability of R equal to 1, which is 2/8, times just the probability of U is equal to 2, which is 3/8. So you wonder if 3/8 times 2/8 is equal to 1/8. And again, the answer is no. All right. So notice that you can always go from a joint distribution to marginal distributions. Okay. But if the only piece of information you were given were the marginal distributions, could you take these two tables on the right and go and get the table on the left? No. The only way you can do this if someone actually tells you or you know that x and y are statistically independent variables. I can always go from the left to the right because I can always get just the p of x from the joint distributions. I can get just the marginal distribution of y from the joint distribution. But I cannot combine the marginals into joint unless someone tells me that x and y are stochastically independent. Integration. So you remember, of course, the derivative, and you, of course, remember the differential. The integral is the antiderivative, and we use the quote-unquote these symbols, these snake symbols. So what that means is, since integral is the antiderivative times antidifferential times differential, of course, gives you the function. And the answer comes out to be, by definition, when you integrate the quote-unquote derivative multiplied by the change in x, you of course get the differential, which of course integrates to give you the function. In integration, once you read Martin Osborne's tutorial or from undergrad, you remember that these are known as indefinite integrals because there's no limits over here, in which case the answer is the function plus a constant c. Why? Because if I now differentiate with respect to x, I have to get back the original expression there. So if I differentiate with respect to x, this will become f prime x. And if there was any constant, when I differentiate the constant with respect to x, that becomes the number 0. If I have definite integrals, I'm going to use really crappy notation. I'm going to get back the original function, evaluate from the upper bound of upper limit of a, lower limit of a, which means I evaluate f at the upper limit b minus the f at lower limit a. This will not make sense until I do an example, which I'm about to do in a few seconds. Let's try to help you out a little bit. I have a function x to the power n. I know the derivative is n times x to the power n minus 1. Can I use quote-unquote first principles to work out the integral? So what's the integral of this expression right here? Remember, I have to get back an expression which, if I differentiate, gives me back the original function over here. I'm going to now do the following. I have to know that ultimately I want to differentiate with respect to x. and I want to get back exactly what you see over here, right? So why don't I add a number? And I do this because I know that right, if I add a number here, um, and if I also at the same time take this number that was pre-multiplied n and then divide by n, why does that work? Because what you've done is, the trick is, take whatever number is sitting in the power of x, add 1, right? So that'll give you n minus 1 plus 1, which is simply n. And then what you do is you divide by that number n over here as well. And you can see that works because n divided by n becomes 1. This, of course, was x to the power n minus 1 plus 1, which is n minus 0, or x to the power n. This works now because if I differentiate this, I get n xn minus 1. So in general, if somebody says integrate x to the power k, add 1 to the power, just like I did over here, and then, of course, divide by whatever remains, which is k plus 1, that would give you the original expression. It's pretty obvious that the integral of 1 over x, of course, is log x. Integral of ex, of course, is ex. These are, of course, indefinite, so you have to add a constant c. And if you read Martin Osborne's tutorials, it's pretty obvious that anything that takes this form gives you this as the answer. So let's now go on to continuous random variables. So notice that here I don't start the joint PDF and then extract the marginal PDFs. If you got the intuition behind marginal PEMFs, the way I did them was I took the joint PMF and I summed across the values of the other random variable to get the PMF of, let's say, x. In the same way, this is kind of intuitive because if you want to get just a distribution of x, you are quote-unquote summing across the values of, my bad, sorry guys. I'm not deriving the marginals from the joint. I'm simply stating the definition of a marginal PDF. It simply says, you're using a symbol right here, so sometimes you use f subscript x to remind the reader that this is a PDF of x, or simply f of x. This simply says the following: the chance that x is some area is integrate the density for that area, and the total area of the density has to be equal to 1. Here's what it means in plain English. Here's a density, f of x. If you want to find out the area that x, the chance that x lies in a certain area, so let's say x is between -1 and +2, you would then take you want to find out the probability of x is between a number a and a number b. You would find out the total area under the curve between a and b, the density. So what you have to do is you have to integrate that density between a and b. By definition, if you ask me the probability at one given point, you would then have to bring these a and b's together so that if you bring the a's and b's together, the area under the curve at a point, of course, is 0. So there's no the probability of the needle in some sense stopping at exactly some value x0 is 0. And by definition, this is take any density, the total area from minus infinity to plus infinity is always going to be equal to 1. So, for example, if you want to find out the chance is between -1 and +2 over here for this particular density, here's how you would do it if you knew the equation of the density. Don't worry, you're not going to get these things. Well, actually, now that it's open book and you can use Wolfram, I guess it is now a possibility that you could get this on the exam, right? This is the normal density. One thing that really is extremely important when you work with PMFs, discrete random variables, the heights are the probabilities. When you work with densities, the heights are not the probabilities. The probabilities, in fact, are found by the area under the curve. Let's just do an example. Here's a density that takes on the value 0, right? Anywhere from, as long as x is between 0 and 4, the density there's an equation. And anywhere outside that, the density is equal to 0. So the joke here is, how many months will it take you to remember this material from this course? So right now the course ends, quote unquote, high probability to remember the materials, and as time goes by, going down, and 4 months later, no one remembers anything. Notice that you're not given the value of c over here. Now, one way to find the value of c is to play a dirty trick. The total probability, of course, under the density has to be equal to 1. So the area of this triangle has to be equal to 1. So you could have done the half base into height equal to 1 and found that c is equal to 1 half. But you should use integrals because you want to get practice. You know that this is the equation. This is a pretty standard expression. Remind yourself that the total probabilities must be always equal to 1. In particular, what I'm doing is I'm not showing what I should have really done was to say the following. I should have said the integral from minus infinity to 0 plus the integral from 0 to 4 plus the integral from 4 to infinity. So what I should have done was I should have broken this up into 3 parts. But then I would never finish making my slide. So what I've done is I have left out the part that says minus infinity to 0. Now I've left out the part that says from 4 to plus infinity. And I've left in the part that says give me the integral from 0 to 4. I know that area has to be equal to 1 when you integrate. So integrals are like derivatives. Integral of a sum or difference is the sum of the integrals or the difference of the integrals. So I can pass the integral through. I'm now taking definite integrals. So c is the number that comes out. When you integrate the number 1, it becomes x, which is from an upper limit of 4, lower limit of 0. Take the number 1/8 outside. Integrate x, which becomes x squared over 2, upper limit of 4, lower limit of 0. And what that means is x evaluated 4 is, of course, 4 minus x at lower limit of 0 is 0. So 4 minus 0, of course, is 4. And this, of course, would be 4 squared divided by 2 minus 0 squared divided by 2, which, of course, is, I guess, well, we're going to this expression that's equal to 8, right? Do the whole thing, c is equal to 1 half. So you found out the value of c. Once you have the value of c, if somebody says, what's the chance that you'll remember this course between 0 and 1 months, the area of the curve would then be found as the integral between 0 and 1. You should do this by hand. You should, of course, do this also by Wolfram. Now I'll do joint PDFs. These are now, you're imagining now x and y being jointly distributed. The total area under the curve is equal to 1. For those of you who really care about how integrals are written, when I state double integrals the first time, I will be very careless. I'll simply say dx dy. I'm not really going to care about the order unless I'm going to carry out the integral. Here's a mysterious, nasty little joint density. It says x and y have a joint distribution where the density takes in the value 0 except for whenever x is between 0 and 1 and y is between 0 and x. This is really, you have to be very, very careful. It did not say x is between 0 and 1. It did not say y is between 0 and 1. It said x is between 0 and 1 and y is between 0 and x. So the way you read this, of course, is something like this. Maybe we can help you out a little bit. X can take any value between 0 and 1. But once it takes a particular value, y must be between 0 and whatever this value is. Since this is the 45-degree line, y must, for any given value of x, y must be between 0 and x. That's exactly what you see here. Y is between 0 and x is between 0 and 1. That's the way to look at this, right? All right. This is equal to a times x. So this is like a cake slice. The height of this cake slice is proportional to x. So it doesn't get steeper going vertically. It gets steeper and steeper going horizontally. So it's almost like this thing is getting higher and higher and higher and higher over here, right? You don't know the value of a. You're asked to find out what it is. So you start with definitions. The total area under the curve must be equal to 1. Now we have to be a little bit careful. To find the total area under the curve, I can, if I go back to the previous slide, I could have gone I could have mathematically first decided to sum up across the x's, then across the y's, or I could have done across the y's and then the x's. So what I've done is I've decided to integrate across the x's first and then across the y's. What that means is I realize that x is going, it takes in a value between 0 and 1. Once I pick a value of x, I want to integrate y's between 0 and x. So that's why you see here. I see that I'm going to integrate across the x's. X's go from 0 to 1. So even though I'm saying I'm doing that first, the outer integral actually is over here. So I'm going to sum up across the x's, which go from 0 to 1. That's 0 to 1. For any given value of x, I then have to sum across the values of y's. Well, then y must go between 0 and y, between 0 and y. And y is, of course, equal to x at that point. This gives you y must be 0 to y must be equal to x. So once again, x's must be summed, x can first sum across the x's, which go between 0 and 1, 0 and 1. Once I pick a value of x, sum across the y's, and the y's go between y is equal to 0 and y is equal to x. Because the inner integral has to be carried out first, what I've then done is, let's hope I don't bungle this. The mouse has disappeared. Nice. Great. This is just one of those times. Where is the mouse? Sorry, guys, I have to use my... let's try one more time. Okay, so because the inner integral is being done first, I've rearranged these terms so that only this is what you are going to integrate first. That's why I moved the dy's up front. So the term a is a constant, so it comes out. So I'm left with this entire thing you see here. This is your, I'm going to carry out, this is your integral respect to y, right? So I've done this. Here is the, oh shit, of course I knew I was going to screw it up. This is the answer right here. Because when you integrate this, the number 1 respect to y, the answer is y, which must be evaluated between a lower limit of 0 and an upper limit of x. So I've done that for you over here, and that here. Upper limit of x minus lower limit of 0. When you multiply this whole thing out, it becomes x squared. Now I'm integrating with respect to x. So x squared integrate will then become x cubed. Remember, add 1 to the power, divide the same power. X cubed divided by 3. Upper limit of 1, lower limit of 0. And that comes out to 1/3. Rearrange, and the answer comes to a divided by a is equal to 3. You should, of course, see if you get the exact same answer for a had you integrated across the y's and then across the x's. Now that I've shown you how to get joint PDFs, I can now show you how to get marginal PDFs, how to pull out just the PDF of x and y from that of the joints. To get just the PDF of x's, integrate the joint across y's. To get just the PDF of y, integrate across the joint of x and y with respect to x. Example, here is the joint PDF between x and y. Again, if you want just the density of x, it's almost like asking if I were to collapse this entire density onto x, what would the PDF of x look like? So you're collapsing this whole thing over here. What you want to do is, for any given value of x, you're summing across all the possible values of y, like this, just like you did for the discrete case. The way you do this, of course, is take the joint density, and now sum across all the values of y. But remember that for any given value of x, given this value of x, for example, you're summing across what values of y? 0 to x. Pick any value of x. You integrate from 0 to x. That's why you go 0 to x. And so you have a joint density, integrate, and that's the answer right here. So this is literally the equation of the PDF of x. It's only defined between 0 and 1. How would you check it as true? you would integrate this creature one more time from 0 to 1 and find that the answer is equal to 1. In the same way, you have a joint density of x and y, and you want to find out the density of y. So pick a value of y, and you want to sum up all this density from over these values of x's. For this value of y, what are these values of x's? It's from this point onwards, which is y is equal to x to 1. Pick this value of y is equal to x, all the way to 1. That's why you see x integrate from here. So I've not done it for listed the integral out for your own purpose. When you carry it out, you're summing from y is equal to x is equal to y is equal to 1. Do this, and that's the equation. Okay? So this will give the density for y's. How do you know it's actually legit? If you integrate this expression from 0 to 1, you'll find that the answer is 1. Here's another one. So again, to find out the density of x, I now take any value of x and sum across all the possible values of y. You can see that the support, right, is just a square. They're not y's and x's are not intertwined. So any given value of x, I have to simply integrate from 0 to 1. So I can get this, take the joint PDF, integrate across all possible values of y from 0 to 1, you get this. To find the PDF of y, integrates across all values of x with respect from 0 to 1, and you'll get this one right here. Conditionals. Conditional means that, going by that example we did right here, if y took a certain value called y0, what then would this distribution be? So this particular distribution would only be defined for this value of x, which is of course y0, all the way to 1. This distribution would only be defined for that value of x, which is from y1 all the way to 1. So when somebody says, give me the distribution of x given a certain value y, you trying to find the equation of this expression right here. What's the distribution of x given a certain value y? To find this creature out, you will use quote-unquote Bayes rule, but you'll remind yourself this only valid for values of x's from that value of y to 1. So yes, the answer to this question is yes, it does depend on the value of y. Let's do an example. We already know the joint density between x and y. I already know the density of x and the density of y. Someone says, given the density of x, given a certain value of y. So you're asking for the equation of this thing right here. Given a certain value of y, what then is the equation of this thing right here? Simple. By quote-unquote Bayes rule, take the joint density divided by the marginal density of y. So take the equation of joint density of x and y, 3x, divide by the marginal density of y, which is 3 into 1 minus y squared, divide, and this is the equation. So 2x minus 1y squared is the equation of this graph right here, but that's only valid from this value of x, which of course is equal to y all the way to 1. So it's telling you that x can only be, the lowest value you can possibly take is value of y, the highest value you can take is 1. So, and by the way, easy way to check this if this is in fact correct is integrate this expression from 0 to 1 and find that the area is of course 1. In the same way, how do I do this? Given a certain value of x, I want to find the equation of this graph. That means I have to be mindful of the fact that it's only defined for what values of y. From 0 to this, which of course is x. 0, x0 I should say. This one, I want this equation right here. It's only defined for what values of y from 0 to x1. And again, it's done very simply. To find the equation of y, density of y given x, take the joint density, divide by the density of x. Joint density is 3x, marginal density is 3x squared, is 1 over x. So this equation is literally 1 over x, but it's defined for what values of y from 0 to x. And that's exactly what you see over here. And the way you'll find out this is in fact a valid density is to integrate 1 divided by x for values of y from 0 to 1. Excuse me. And same thing I did with the joint cases right there. Now I'm doing with joint PMFs. I'm now doing for PDFs. How do you know that two random variables, continuous random variables, are independent? If the joint density can always express as the product of marginal densities, or when the conditional density is simply a density of y, as in this particular case, you know they're independent. Quick example. Is this independent? Ooh, interesting. So what you're asking is, pick any point right here. Is the density here in terms of x and y equal to this thing multiplied by that thing? So this thing right here is 6x squared times y. This is 3x squared multiplied by 2y, and voila, that is equal to 6x squared y. So it is x and y in this case are stochastically independent. Why? Here's why. Pick a value of y. Notice that this is your density of x given y. That is the exact same shape as over here. Makes no difference, right? So you can see that those conditional densities don't depend on the value of y. Similarly, I mean, I don't want to abuse this picture too much, but if you went this way, you can see that conditional densities of y given x's would also have exactly the same shape because the support is a quote-unquote square. So it's not a surprise that in this picture, x and y happen to be independent variables. That's not true over here because, as you saw previously, the density of x given this particular value y is completely different from the density of x given that particular value y. So take this number right here. That density isn't equal to this thing multiplied by that thing. And you can see that there's no way this 3x squared times 3 over 2 1 to 1 minus y squared, there's no way that's going to be equal to 3x. And you can see that therefore x and y are not independent. But the intuition was you can see that the support is not a square, it's a triangular. So the conditional densities are going to depend on the values of y and x's. That's why they're not independent. That's the intuition behind this. Thank you very much.